what we have is that hardware knows what is happening now, and it knows if there are cache misses to certain addresses. And the compiler knows what the program will do in the near future. So there was a study that checks how it can be this information can be combined, and the purpose is to avoid cache misses and to avoid instruction overhead in the case that there are no cache misses. Okay, so say we have this situation. We are in a loop, and so this lower and upper bounds, they do not have to be constants, and how much we increment the loop variable is not needed to be a constant either. But so the compiler doesn't have to know at compile time how many iterations will be used, but it can calculate it just before the loop. Okay, so say now that there is a cache miss to an element in the B array. And if it's a first level cache miss, it will take a few tens of clock cycles. So it's not much, there is nothing, it's not very much time to do something useful. So it just waits until the data arrives. But if it's a level 2 cache miss, it will take several hundred clock cycles. So why not do something useful while waiting? Okay, so if we consider the programmable prefetch engine that is available in Power, why not program it in when we are waiting for the data? Okay, so how can we somehow jump to code when we get a second level cache miss and enter some parameters to this prefetch engine and then jump back and wait for the data? Well, one option which doesn't work would be to use a performance monitor counter, and it can count the number of events that happened, and if it's a cache miss that we count, then we could regard it as we have got just a new cache miss, but it is too much overhead. But what we can do is to change the hardware, if we produce the hardware, to get a so-called lightweight exception. Normal exceptions, they are invoking the operating system, and that takes by far too much time. But if a level 2 cache, not level 1 cache, because that will be too quickly served anyway, but at an L2 cache miss, then we can take such an exception and jump to some code that is part of the function. So say this is the function, and void, okay, we don't do much, and then this is what the program has written, but the compiler can produce extra code here. Okay, and when there is a cache miss, the CPU will jump to this part as part of servicing the exception. And then this exception handler can figure out what to do. Which reference to that got the cache miss, and it has the program counter, so it can know that. And if there are multiple loops, there could be extra code for each loop. Okay, so it's quickly to find what to do when there is a second level cache miss, and the compiler can do that. Now the question is, how can it know how many iterations to prefetch and the stride? Well, it has all that information, since this extra code to program, I should write, to program a prefetch engine. I can promise you I didn't, okay, it was I and Michel Dubois who made the study, and I didn't use this long variable name or label name, but well, that's not very relevant, but since this is part of the function, the code here has access to all the local variables. So for instance, it sees the same local variables, and they are register allocated as with the rest of the function. So this is very convenient to program it, since it has all the relevant information. The only difference between always programming and not always programming is that with such a lightweight exception, it can program the prefetch engine only when it's needed, and it knows exactly how many iterations that will be run. Okay, so for codes like this one, this turned out to be quite useful. Okay, so how is things like this evaluated? Well, of course, not in hardware, because this hardware doesn't exist, but we use a simulator that can estimate with good enough accuracy what a new hardware feature will how useful it will be. That is far quicker than producing the real hardware, obviously, and less expensive as well. Okay, so in summary for this video, there is a big complication in data prefetching, namely that we don't know whether there are cache misses, so it may be a total waste to insert prefetch instructions, and the hardware knows it, and somehow this information can be combined. And if we do that, we can get the benefits of programming, of prefetching without the negative parts. Okay, so what will I ask in the oral exam about that? Not much, but basically this point. This is how it can be exploited, but it's I will not ask about it, but it can. Okay, maybe I should have said that before the video, but I think it's too detailed, and so I don't want to ask about it. But it's good to know about this.